Welcome to the SEG Europe Regional Advisory Committee's webinar series, State of the Energy Industry in Europe. Dr. Adriana Ramirez, Chair of the SEG Europe Regional Advisory Committee, and myself, Lori Weitzel, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short presentation followed by a question and answer session. During the question and answer session, you can enter your questions in the Q&A box, and you can also raise your hand and I will move you where you can ask your questions directly to the presenter. Our presenter today is Erik Finnstrom. He was educated as a geophysicist at the University of California, earning his master's degree in 1981. University was followed by an international career in the oil industry, working in Chevron, Norsk Hydro, Statoil, and EQUINOR, and TGS as an explorationist, researcher, manager, and executive. Job focus and responsibilities have varied over the years, but understanding the Earth's history and the structure through the integration of geophysical data and geologic principles has always been a fascination. Erik's most recent positions were as Senior Vice President for Exploration Excellence in EQUINOR, and then Senior Vice President New Ventures at TGS, have led to an interest in what artificial intelligence can do to increase both the efficiency and effectiveness of exploration for hydrocarbons. Erik currently is indulging his interest as an advisor, mentor, and minor owner of a startup, Cognitive Geointerpretation Inc., which is developing a portfolio in these areas. Without further ado, please welcome Erik Finnstrom.
Thanks, Lori, and thanks, Adriana, for inviting me to do this. So that background certainly explains, what I'm about and why I decided to talk about this particular topic. I guess what I would say, just as maybe a disclaimer at front, is that this is something I'm interested in, and I do have some knowledge of artificial intelligence and so on, but I'm by no means an expert. I guess I could say I'm somewhat of an expert in exploring for hydrocarbons in the classic sense. So this is going to be a marriage of those two things, and maybe a look into the future of my take on how you can apply AI, both now and in the future, to do a better job in exploration. So here's kind of the way I'm going to go through it. I'll give you a few thanks to the folks that I've spoken to and have helped on this and who've given me some data. And then, all sorts of things are happening. The world is obviously in a pandemic. I'm sitting here in my kitchen in Oslo, Norway, and probably a lot of you are at home and such. That's part of the context of exploration. Also, the long-term energy transition that we're going through is part of that. The performance that we've had through the last maybe decade of exploration is part of that picture. So why would we need to do exploration in that context? That's something. And then again, AI. So I'm going to try and answer that, at least what I believe that we will need to do it. And maybe the best way to do it in the future will be to combine in artificial intelligence. I'm going to give you a few examples and then talk about what I think the industry is doing and the discussions I've had with some of the players in the industry. And then give my speculation on what a workflow would look like and how it would function using AI extensively. So thanks, first of all, then to all these folks here, Piyush, who I am, as was said, I'm working with in cognitive geointerpretation, and Arvind, my old colleague in TGS, who I've had quite a few discussions with about AI through the years, and also now recently, he's loaned me a little bit of data. And Mark Brownless in Geoteric, who are doing some really nice work, and I have had some good discussions with Mark on what they're doing. And also thank you very much to Matt Johnson of Chevron. It's not that easy necessarily to engage with the folks in oil companies because they like to keep their play a little bit close to the vest sometimes. But Matt's been very cooperative and helpful in discussing what Chevron's doing. And finally, Mike Wynn and Graham Johansson in IHS Markit, who gave me some up-to-date performance data from the European basins that I'll show you. And then to acknowledge Rystad Energy, EQUINOR, and DeepMind, who I have not spoken to, but I've taken data off their websites and incorporated it in this presentation. So just in the title, I had the words efficient and effective. I just wanted to clarify what I'm thinking there. Obviously, efficient is to do something with maximum productivity and minimum wasted effort or expense. So in our context, exploration context, more prospects and wells with fewer or the same resources at least. And to be effective means that you're successful in producing the intended result. And again, in our context, that means identifying the prospects with the best chance of success so that you can drill those, and that you also correctly predict the volumes on the average of those that you do drill. So that's what we'd like to do, and it's always what we'd like to do, but we'd like to do it all better. So that context that I spoke of, this is taken off the web from CNN, I think in April when I started thinking about putting this together, and then, you know, things were happening, but the fall hadn't been as sharp as it ultimately would be. So their data drops it down to oil demand from 100 million barrels to 90 in a very short time frame. But in fact, from the point of this plot then forward, we had an incredible precipitous drop down to about 72, 73 million barrels per day of demand. And if you see the plot goes from 1986, right, to today, with basically an almost uninterrupted continuous increase in demand for oil globally. Even large recessions, economic recessions, have only made small dents compared to what we are going through today. And then I've taken data, as I said, from Rystad Energy, who I think really do a nice job in analyzing the global oil situation. They've also turned their attention to the pandemic and put out some, you know, publicly really nice analysis of what was going on. And this is from that, from their website again, where they're looking at the recovery that already as you hit that bottom, then they are looking at the transportation rates that you can get, cars, planes, these type of things, global activities starting to recover. And then they're projecting that forward, depending on what's happening with the pandemic globally, how well it's contained, a couple different scenarios. But they see this kind of R-shaped recovery, so that we're coming back eventually to maybe our 2019 level of around 100 million, maybe not, but potentially in 22, 23. So the total demand rate on hydrocarbons and oil particularly has really taken a hit. It will recover though. It will recover, I think, certainly out of that deep depths that it was in. Then what we know from past experiences, and we're seeing it again from Rystad Energy, the investments change almost instantaneously with such oil price drops. And you can see then the total investment rates that are based on data that they've gathered from the companies, dropping again enormously, just like the price from 2019 to 2020. And then kind of the dots, the orange, or not dots, but little squares show what it would have been potentially without the collapse, the investments. And it's showing, as they do with their sort of R-shaped recovery on the demand, they're showing investments recovering to similar levels of 19 through 22 and 23. But the great drop will definitely bring the production of hydrocarbons globally down going forward, and there'll be a gap that there wouldn't have been if this hadn't happened. So rather than being an oversupply, I think potentially they're showing that in some kind of time frame here, there may be a shortage. In the background for all of this is also that we have an energy transition ongoing globally, and I think EQUINOR, my old company, does a very nice job of looking at this in a scenario-based aspect. I think other companies do the same and publish. I think BP, Exxon, I think they put things out, but this is one that I'm familiar with. And this is a big piece of work, hundreds of pages of analysis, and I've taken out one page from a presentation that they published. But this is the oil and gas demand scenarios along with the supply scenarios, so-called legacy supply scenarios forward to 2050. And what they do is they make 3 scenarios depending on global economic development, political developments, technology developments, etc., sort of population developments, everything that can go into technology developments, everything that can go into a demand curve. And they do 3 scenarios. One that is, in a way, you might say pessimistic relative to CO2 and global warming, where oil demand actually continues to increase. And then the most dramatic one is the bottom blue, you can see on the graph, light blue. I guess I can point. So this is the most dramatic one, where there's a global consensus on CO2 policy and technology develops, etc. And we have a very hard transition off of hydrocarbons. But even so, what they also do is take our current supply and they apply the known decline curves to the existing fields and don't put any investments in, and you're going to open up a gap. So it shows that no matter what happens in these sort of scenarios that they can come up with, both oil and particularly gas on the right side will have large investment needs, again, regardless of the kind of energy transition that happens within what I would say and what EQUINOR would say are realistic scenarios. So I'm trying to make the case that there's a lot of stuff going on. Price of oil is dropping. We have uncertainty. Investments are being cut on certainly all of your companies that you're out there in oil companies, your exploration budgets are being cut. But I think in the, let's say, at least medium term, there's definitely going to be a need for exploration. Then if we look at how are we doing when we do exploration, what's our performance? I think that's a bit of a problem. I think it's less of a problem that we have an energy transition for the industry. The problem is that we're not doing very well overall globally in our efforts to explore for oil. So this is from Europe, because this is the European section. I've gotten from IHS. Thank you very much again, IHS. This data for the number of wells drilled on the left per country. Norway is green, UK is blue, all others put together in Europe are the gray. So you can see Norway is holding up the fort, you might say, or holding the fort on drilling and keeping up the drilling activity through time, through the decade. But the same for Norway as is for UK and the rest of Europe. The actual results from that haven't been great. 2010 and 11, I think, are the Johan Sverdrup discoveries. Other than that, not a lot of oil and gas being discovered. If we look globally, this is global oil discovered in the dark green, and it is our oil consumed globally in the light green. So what you see is through time from 2013, these are the numbers I could again pull out, taken from Rista and also from IEA. And I would say the consumption ones are very roughly kind of distributed by myself on this plot. But a steady increase over time of the amount consumed to what we had at the end of 2019, beginning of 2020, of almost 100 million barrels per day. And that then calculates out to 36 and a half billion barrels per year used. But if you look at what we find globally, that isn't anywhere close to that. And it's pretty much a trend going downwards with time to 2019 being something around 5 billion barrels globally discovered. So a widening gap opening up between what's consumed globally and what's discovered globally. So this is something I'll come back to. This is what I call a classic workflow. So how are we doing this exploration? Traditionally, I think we've built up, most companies built up something like this. This is very generalized, but represents, I think, what you do. Going from left to right, data coming in from acquisition through processing imaging, often taking, we're talking then, let's say our kind of assumed data set that I'm using to speculate on is a large, rather large regional 3D with some plays established, maybe some speculative plays, maybe one well, and that we turn a couple interpreters loose on it, and we'll also be through this chain, we'll be using some specialists, some petrophysicists, some structural geologists, some AVO guys or girls, and that type of thing. So traditionally, again, we're going to waste a fair amount of time just getting that data in-house and getting it loaded. Then we're going to do what I call a framework interpretation of horizons and faults. We're going to do various sorts of analysis to bring out other attributes in the data and try and build up a geologic model from this work. We'll be building up charge models and sealing models. And from all of this work, we're going to try and make some prospects. Then we're going to rank and volume, calculate volumes, risk, and rank them and plan a well. So that's kind of typical flow. And I'm just going to move this, and yeah. So I mean, this is going to take, I say, in my experience, something like this on a large 3D, going to take 1 to 1.5 years from my little dashed line, not including the processing and imaging. And you might come out with, of this, what you would consider good prospects, who knows, 2 to 4 or 5, maybe, I don't know. And you probably will do, on the best one, one well plan. So that's what I would say is kind of a typical workflow for a big 3D. How can we do this better, and why should we use AI, as I'm postulating or kind of saying? I think that AI will help us. When you look at these blocks, when you look at these blocks, and again, you know, this is very kind of generally defined, but these kind of blocks of time, a lot of that time is going into finding data and kind of bringing data into the analysis and getting it ready, finding it, getting it ready, incorporating it, synthesizing it. And if you don't want to spend the time, well, then you don't. But then, of course, your analysis isn't nearly as good as if you did spend that time. So I think that AI will help us ultimately find and use much more relevant information and data. We'll bring in analogs, we'll bring in property distributions, all the kind of things that we have as, now I'm thinking as the kind of a bigger oil company, that you have in your files of experience for the last 50 years, say, you can bring to bear on this. Also, hopefully, sort of globally readily information much more easily. And I think that I can't really prove it, but I'll talk a little bit about it. I think that AI will do a more complete analysis of the data that you have. You'll be able to create more models in shorter time frame, and your AI algorithms will operate on more of the data than you ever could as a human being. So you'll be able to bring in more, you'll be able to make more models and use more of the data rigorously, which allows you to create your basic building blocks of your model much, much faster, so that you can get your kind of ideas up quickly, discuss them, and continue on, rather than kind of lock yourself into a model as you plow through the data. And this is why I say you can remove bias, because, you know, those of us that have worked in the industry for some time, we build up an experience base that's based on what we have, data we've seen and things we've done, and that's just the way it is. But that also creates a bias in when we look at data in the future. I think that the machine learning will, in a couple ways, help you remove bias. It'll, through the algorithms themselves, will be incorporating more data. But I'm also going to talk about how you can work in teams to get discussions up, as I'm saying, more quickly and consider more models. Ultimately, I think that if you have good AI routines, you're also actually going to be building and retaining institutional knowledge in a better way than we do today. So, okay, AI is great, but of course there are dilemmas, as there always are with everything. And I'll come back to this, but to get a good working machine learning AI algorithm, you need a lot of data to train it, for it to learn, to train. So that's one thing. I think oil companies, big oil companies have that. Maybe not everybody has that. I think some of the contractors that's still doing good work, they don't have as much access as the oil companies do. The other thing with AI, I think, is that it is maybe the thing that might be most disturbing. I don't know, but you don't really know how it comes to its conclusion, right? I'll talk a little about these neural nets, but how does the neural net actually decide that the answer is the answer that it's going to give you? You don't have a good insight into that, which means that it's hard to understand if it's giving you artifacts or wrong answers. This is going to eat computer capacity, so you're going to need a lot of computer capacity, which means it's going to cost you money. So you have to be willing to invest, and that's kind of a question and a dilemma. Will oil companies be willing to invest the money that it'll take to do this successfully? And then again, another question around that is, do the oil companies have enough expertise within artificial intelligence, and can they even get a hold of it if they want to be able to do this effectively? And finally, now there's a lot of negatives here, but let's face up to the facts. If we can do it, it would be a true paradigm shift. It would be fantastic. It would be fascinating. I think I would want to go back and work in the industry again as a young person. It would be wonderful. It would be starting over, which for people that are kind of along in their term of service, it's going to be difficult. And it's going to have, companies have a lot of inertia relative to making huge paradigm shifts. So it might be tough, but I think it would be so, well, that said. So let's just define a little bit more closely what it is we're talking about. Talk about some of these AI definitions and so on. So there's two big categories of AI. We have the artificial narrow intelligence and artificial general intelligence, and I'm only talking about the first one, narrow intelligence, where we design an algorithm to solve a specific problem, like you see in the picture, like we know about today. Assisted driving in our vehicles, recognizing what's going on around it, and so many other things. There's now hundreds and hundreds of examples that you could put up here, but that's one. The other one is, I think, general intelligence is let's say, still hypothetical, still science fiction, but it's being worked on. And so I'm not talking about the Terminator here. So I've started to use the terminology already. AI, machine learning, neural networks, deep neural networks. So this is kind of the hierarchy of it, how it fits together. And I do apologize for mixing it all up, but I think that's basically what happens, is that people that talk about it mix it all up and assume that you know what this means. And I'm sure anybody out there that's worked with AI at all knows this. But let's just clarify. So overall AI, machine learning is a technique within AI. Really what we are going to use to solve our problems are deep neural networks, kind of the most embedded thing here, which is a form of AI, which is a form of machine learning. So what is different about this, and why do I talk about needing data, needing interpretations, which is an interpretation in our world is labeled data in the AI world. They talk about labeling their data so that you can train with it. That's what you need. We need interpretations. And why is that? Because this is the way it works. I mean, our traditional programs that we've always used are like the top one on the left. We have an input, a seismic trace, say. We operate it on it with a deterministic scientific physics-based program, and we get an output, some other form of that trace. Machine learning is such that you give it the input and the output. You tell it, as this thing over here shows, you tell it, okay, you tell your neural network, you tell it this is a dog, and then you give it a bunch of pictures of dogs, and you say, these are dogs. This is a cat, and many pictures of cats. These are all cats. And then you tell it what they're not, other things. These are not cats and dogs. And then it figures out, you might say, how to classify these things within the neural network space, and how in the future to identify a cat or a dog or whatever it is you're going to identify. And these are kind of simplistic ones that you've heard. I think an interesting one that Arvind Sharma gave me from TGS that he likes to use is this of the baseball player, which really kind of gives you the feeling of how it works. Is think of the hitter as the neural network, and the baseball hitter isn't solving any physics problems, anything like that. It's trial and error. The ball is pitched to him, he swings, either hits or misses, and he corrects and tries again the next time. And different inputs with different types of pitches and pitchers, etc., come at him, and generally that all goes into his own neural network and gives him a model representation of how to hit the baseball. And that's really what we do when we train these algorithms to recognize things and to come up with solutions for us. So let's check my time here. Okay, it's not too bad. Why is, I mean, AI is kind of blasting off since, I would say, and I'll show you why, since about 2012, really, I think is kind of like the big blast off. It's being used all around the world, much more than we are using it, I think, in oil and gas, and particularly in exploration. What is it that's enabling that? I would say first and foremost is the power of the computer and GPUs, which we also do use in oil and gas, the GPUs that we use to do seismic imaging. These things have made a tremendous difference in being able to do the computing necessary for developing the deep neural networks. Also, the kind of the Silicon Valley approach that where AI has kind of blossomed, of being open and sharing and having these open source toolkits, I think has really spread this thing. And related to that, kind of the research and development that's published, a lot of interesting work published. And for us, the last two things I think are for us, you might say, we have in oil and gas massive amounts of data. And as I said, oil companies at least have it interpreted or labeled, as you would say in AI. And we also have begun on our cloud computing and data lake kind of journeys, which is facilitating getting a hold of that data and easily getting it into AI algorithms. So these things are both facilitating what's happening globally, but also will hopefully facilitate this explosion now within exploration. Looking at how is this kind of developed, it is, I've really mentioned it already, is, well, over on the far hand right, really the first sort of neural network idea of how this worked was developed first around 1957 to 1960. And this has kind of gone back and forth and up and down and languished, and not really much happened until, honestly speaking, until 2012, where we had the introduction of the GPUs to solving the problem. And then the acceleration of how many GPUs could be used in training the models from, in this kind of 1 to 8 to 10 to 100. And now, as we go forward, more kind of working with the chips, making each chip better incrementally, but also working with algorithms and ways to solve the computer problems with algorithms to make it run faster. You can see kind of the development. This is solving a benchmark image. I think this is very well known in the AI circles, that this is the amount of error in the image, and this is a number of layers used in deep neural networks. So you kind of go from, at this point here, to what you would really call deep neural networks, and now 152, that was in 2015, we're up in the thousands today. The error isn't that much lower, from what I understand, maybe in around the 1 to 2% range. But this is kind of what's happening in terms of the development of how these problems are solved. And again, looking at the computing, which I say is, let's move this one out of the way, the most important is a plot where you're looking at how much compute do you use to train one single model. And the literature is saying to me that that is the single most kind of important parameter that's correlative to the power of the model, is how much compute can you use to train that model. And and it's been increasing from 2012 exponentially. So you have roughly an increase of 10 times per year in compute per training run that the kind of most powerful models are using. A lot of people have heard of this, the Google company, DeepMind, that's creating these alpha algorithms, and AlphaGo, which they created to play Go, the game of Go, which is thought to be one of the most complicated things that you could attack with a computer program. That easily now defeats any human being, and has also come to the point where it has taught itself, without any learning examples, to be better than the original AlphaGo, as an aside. But again, the experts, I think, expect this trend to continue. You can't predict it over, really long term, but a logarithmic or an exponential increase continuing in the short to medium term means that you're going to have incredible powerful deep neural networks available to solve problems going forward. What is it that is going to drive this going forward? I think some speculation around chips being developed specifically for AI solutions, and also kind of working with the algorithms to make them massively parallel and continue to optimize on that side. Check my timing. Okay, not too bad. So this is an example of something happening out in the world that I'm impressed by. There's tons of things out there, like I said, in the literature. It's a little bit hard to pick, but this is again from DeepMind, the Google company that created this, they call it ALPHAFOLD algorithm, that has modeled through machine learning three-dimensional folded protein structures. It takes, there's a lot into it, but very basically, from my understanding of what I read, that it takes some genetic information and is able to use that to model potential, project onto potential 3D folded protein structures. And there's a number of steps, nested or kind of separate machine learning steps in here that end up in this result, which is quite impressive. You see the blue, let's see, it's the ground truth is the green and the predicted is the blue, so they project right onto each other. These sort of things previously had to be solved with laboratory experiments, and they can be now at least these can be modeled with machine learning doing it. That's much, much faster and much cheaper. I think that this is a good analogy for what we'll ultimately be able to do with the earth sciences and exploring, that we can take the data that we have, we can take our ground truths that we know and create complicated models like these. And just to say and to admit that I'm now in a way hyping AI and the application of deep neural networks. I'm definitely hyping it, and every technology has this thing that the GARTNER group describes as the GARTNER hype cycle. I think is very a good way of looking at it. That has, let me see if I can move this one again. Yeah. So going from innovation to getting really excited about it, inflating your expectations, coming off of that as you continue to work with it into somewhat of a disillusionment, and then finally coming out and creating something that is working in a kind of a production mode. So I've taken their one that they had published for 2019 in machine learning and just kind of really decimated it down, just put a few things on there. I think the one that, some of the things that are like relevant to us, I mentioned artificial general intelligence. They have it on there as right at the beginning of that hype cycle, and having, you know, more than 10 years to any type of peak. Cloud services, which we're interested in, toolkits, cognitive computing, and GP accelerators that I've been talking about are out there on the production plateau, where we need something else actually now to come in and boost this. So deep neural networks, which I think were used to solve those proteins, are what we're going to be using, and people are using in oil and gas. But that's in the very early phase, I think, of this hype cycle, or in early phase of development, so that it's probably more on the innovation side than the coming off of the peak, you might say. So it's still probably going up. But to admit, there's going to be ups, and we're going to come back down. But I think if we keep at it, we will get through and have a point where we're actually using this routinely. So I wanted to ground truth my thoughts, and I was lucky enough to have access to these fantastic people here that are experts in the field and working actively with oil and gas exploration, developing software, developing products, developing technology for their companies, both entrepreneurs and people in big companies. So I talked to them and asked them a number of questions around what they think. And I would say I feel good about what I think after I've talked to them, that they were on the same kind of path, that they believe that, you know, going forward, machine learning will push us beyond what we can do, and that it will do much more with the data. And I think this is just summarizing from all of the folks. It'll do much more with the data than we can do today, because we have, it's not a term I've introduced yet, but we have kind of a cognitive overload when we try and bring in too much data. That isn't any problem for machine learning algorithms. They feed on that data. I think Arvind says here is maybe the most philosophical in what he's saying, that we haven't, well, everybody's agreeing that this is going to get us to our solutions faster, save us money, give us better solutions. But he says it's very immature in oil and gas, and we haven't crossed the Rubicon where AI does more than humans. Matt Johnson in Chevron, I'm sure they're doing lots of interesting things. We talked, and you know, I think what he gave me confidence in is something that I believed, is that the oil companies have a lot of data there about what they've been doing, how they believe prospects are, risk, volumes, what they look like, etc., that they're incorporating into machine learning. And they're trying to make machine learning in Chevron a standard for everybody to use. So I think that they are and Matt tells me that this is something that is grounded in the uppermost leadership in Chevron and Chevron Exploration. So it's something they definitely are going to pursue and make the investment into. And Piyush, who I work with on a weekly basis, I think puts a challenge out there. You can see what he's saying. He says, in the end, it's going to be used. You're going to be working from home on petabytes of seismic data, and I'll show you a little example that he's produced with AI tools. And you either adopt, or you get left behind. So that's a challenge to you if you don't believe that this is the way to go. I do, and I think all of these folks believe more or less that this is the direction we're going. So thank you all of those four for talking to me and sharing their thoughts. So I'll give you some examples of how that are available to me. I'm sure there's many more things out there that aren't available but are being developed and used. But this is from Piyush and CGI. And what they've developed is an algorithm to use AI to compress and deliver seismic to your browser. It gives you instant availability of massive data sets. And that is actually based on using AI. So you can see when I show you my next workflow for AI workflows, it's really based on this thought that this data is instantly available to you wherever you are, rather than the sort of loading tapes, blah, blah, blah. That's the kind of old-fashioned way. This is from TGS, and this is showing, again, off their website, this is showing that they're able to, they've created an algorithm that they call SaltNet, which is a machine learning algorithm which is able to identify salt. So it both identifies the boundaries that define salt, and it identifies salt as a body or as a lithology, you might say. So both a horizon or boundary and lithology SaltNet is doing for them. So that's something that's already out there. They're using it to create, to pick salt when they're doing their imaging and try and speed that process up. But I think this is an example that can also be used in the future, and maybe is, for doing your end interpretation and building your models. This is also from TGS. They, part of this algorithm, it picks, this is a different section, not the same as the other one, but you can see again, salt is being picked. I think that, yeah, that's salt being picked in the purple, but also the blue is the algorithm saying, well, this is where I think salt is, but it could be down here. There's some uncertainty. So this thing will give them very quickly both the picture of the complete model of where salt is in this basin, but also where the pick of it is somewhat ambiguous. Now this is from Geoteric, and I'm really impressed with what Geoteric's doing. I don't know everything they're doing on the AI side, but I've talked with them about the faults, and this is really impressive to me, the work that they're doing to map fault planes with machine learning. And you can see this is from their website. You can see the sort of complicated nature of the faulting. They have multiple examples. This is just one, but complicated nature, three-dimensional nature. You look at it, if you're a structural geologist, I think you say, yes, I believe this. This looks like I would expect. But you know also as a seismic interpreter to be able to create a true three-dimensional fault interpretation like this would take a long, long time, and you probably wouldn't be able to make it as accurately anyways. So this is, I would say, a breakthrough from Geoteric's side and an example of building up that framework interpretation very quickly. And I would say, I think this is my last example from industry, again from TGS, which goes to maybe kind of the more numeric side of it. TGS has developed machine learning algorithms to predict logs where they haven't been recorded. So, but of course they need a lot of data in that area to train the algorithm to be able to create those kind of virtual logs. This is from Permian Basin in Texas, where on the left side you have the sonic logs displayed that are recorded, and then you see on the right side all of the well traces where the ones that you see on the left are, but also the ones that weren't recorded as sonic that are filled in through a machine learning algorithm. And you can see that it actually reflects the geology. You can see geologic horizons because the logs are so tightly spaced. But I think you can, in a way, project this to say that you can do this. You can create these virtual logs, but this kind of algorithm will also do petrophysical analysis and other things for you. So you use sort of the numerical extraction or modeling of your geologic data. So to wrap up now, okay, 45 minutes, could have been worse. Classic workflow, we talked about this. This is, again, my experience through my career. Year to year and a half, year would be fast, I think, I don't know, to give you a complete analysis going through, with most of this work being done by individuals and group work being done at the points of peer assists and peer reviews. And so what I'm saying is, I think that I've talked about techniques that are out there, and even ones that have been developed for oil and gas that can do, if we look at the building blocks, what I'm doing here is I'm making, my building block is 1 week rather than 1 month like I had in the classic one. I'm making instantaneous access to the data. I'm indicating that this is a team working of a tight team of experts that is running machine learning algorithms to create these various aspects and reviewing those on sort of a tight time frame, perhaps adjusting and going on, and that each one of these would feed into, in some way, the next one. Kind of like the protein one, if you read the article, there were multiple machine learning algorithms solving for those various parts of the protein structure. I think this is something that the technology is there to do, the data is there to teach the algorithms to do it, and we actually have the kind of expertise that we need. I think that this will make a sort of order of magnitude jump in what we can do in terms of prospecting, that we could do this same kind of data set, the same situation in 1.5 to 3 months, that we could create quite a few bit more ideas or prospects or leads, and we could create at the same time as many prognoses and rankings, etc., as you want. That's my postulation. This is also something I've always been interested in trying to do. It's kind of hard to get oil companies to do it exactly, but I think the most effective way to work is as a team like this, with what you call T competences, people that have deep discipline competence, at least in one area, and knowledge, good knowledge of the other fields. These would be something that this team would be one that I could turn loose on a machine learning workflow. Of course, you could do that workflow in other ways, but I think this might be the best way in putting together a team like this. So let me bring it in for landing, give you a summary. I think we've talked about the pandemic and also the long-term energy transition. I think obviously those are out there, those things are happening, they're affecting the need for hydrocarbons, but I think over time we're still going to need to explore for hydrocarbons. Even now, the lack of investments will probably open up significant gaps in the near future, or in sort of midterm. We're not seeing super exploration or global exploration performance. We need to do something about that. AI, I think, is one solution. If the people that have the money, that run the oil companies, are going to invest in exploration, we have to give them the confidence that we're going to be able to solve the problem. Oil and gas is still early on the curve. So I think you put together the algorithms, the expert teams, it's going to lead to much more data being used and very thoroughly analyzed, which eventually will lead you to many, many more prospects using less resources. So that's what I had to say. Thank you very much if you stayed with the entire time. I appreciate that. And that's my presentation.
All right. Thank you very much, Erik. We have a few questions. The first question asks, what do you think of the tech giants having oil and gas segments such as Amazon and Google? They have the technology and understanding, but they lack the data and probably the experience that the IOCs have. Do you suspect that they will be working together in the future to fill that gap?
Yeah, I mean, I don't think, you know, we've kind of had those in my career. I've had a little bit of those discussions with those big companies, those type of tech giants. And, you know, they keep assuring you that this is not what they want to do. They don't want to become oil and gas companies. So I don't see them in a way competing with oil and gas. I see them supplying the technology and maybe some of the people that go into those expert teams that we would use. I think that to employ this type of technology, you have to have the kind of domain knowledge that we have from oil and gas to do it effectively.
I have one question. So you talked about dilemmas, and there's one dilemma I often think about, and that's the bias, the implicit bias that we have on our training data, because we have been processing it, and the whole processing and imaging process steps have certain biases, and there are a lot of biases by assumptions, limitations, timing of the workflow, etc., but also the labeling. So how do you think that plays a role here? On one hand, I'm answering my own question, but on one hand, I see that the advantages of the efficiency might be enough because you will have a much faster workflow.
Yeah.
But I'd like to know about your thoughts on this.
Well, I think, yeah, I mean, there's a lot of details that I've very, very quickly skipped over here, right, Diana? But in terms of, but I think basically, if again, you go back to the very high level, to beat that bias issue, you just have to have lots of examples. That's why I say the oil companies will have an advantage with how much labeled data they have, so that you have a whole kind of averaging out of ways of looking at it, types of data, etc., that you can feed in as your training data. That's kind of what I think.
Yep. No, I agree. I mean, definitely, whoever owns more historic data and more examples has an advantage. At the same time, there's smaller companies and there's students, and as an industry, we gain from different diversity of ideas, right? What's your view on the need for benchmarks, for industry benchmarks that can provide an objective evaluation for technology that is developed, that is pretty much moving away from physics, that is based on AI type of algorithms?
I think that would be, yeah, I think that would be, you know, something the SEG should probably, and maybe they are, I don't know, should be establishing like the benchmarks that they've had in the past. I think that's the way of the future, is working with AI. And definitely there should be, what is the one, you know, SEAM and these are various things that have been in the past. The same sort of thing should, I mean, I gave the example, it's out there, it's publicly out there, what's it called, ImageNet or something, that one particular, there's one that's been used through the years to classify these image recognition algorithms. We need to have the same sort of things in oil and gas to kind of give the confidence to the users and to management, you might say, skeptics, that we're going the right direction.
All right, thank you. I guess this question kind of tails onto that discussion. Do you think the public available data is sufficient for the industry to find and create good AI enablers? And if only some companies use some data and they move to a frontier area, they would lack good data and need to feed. It would lack good data needed to feed the neural network.
Yeah, I think it's a dilemma. You do need to have a plethora. You need to have that wide kind of base. Again, so I keep coming back to, I think the big oil companies have a big advantage. But, you know, speaking with, say, Piyush, you know, kind of going more into the detail, the technical details, he believes that there's ways, and maybe it's not even complicated, I don't know, but that there's ways to kind of determine that you don't have to use a lot of, some algorithms don't need a lot of training. They can be very effective with just a few, if you find the right examples. You can have the whole world of examples. Within those examples or training data, there's a very small subset that actually give you, that train up your model the best quickly. And then if you have a way of finding that subset, then you have a big advantage. So that's a little bit technical, I think, but I think even small companies, independent actors, if they can solve that little conundrum there, then they can also be in the game, you might say.
Thanks. It is the oil and gas production dealing directly, and they lack the domain expertise. I think this went back to the original question.
It was probably a comment for that question.
Yeah. All right.
Erik, okay, sorry, Lori, go ahead.
Go ahead. As a geology staff, should we focus our work on algorithms or data in AI?
Well, I'm not quite sure where we're going with that, but I think that developing it and using it, I think it needs to be done in the sort of teams that I showed. So you need to have people that really understand how to develop AI together with geologists and geophysicists and the people that have traditionally built up the models. So, but I think every geologist and geophysicist today would be, you know, would benefit themselves to really, if they haven't already, begin to understand how it works, why it works, and what are at least the basics of it. And I think ultimately you're gonna, maybe within 5 years, that the teams you would be expecting that the geologists, the geophysicists would be able to modify and write, you know, create machine learning code. That maybe that's crazy, I don't know, but I think that may be the case. That you get so deep into it. But the starting point is that I think geologists now today, what they need to do is to understand how it works, why it works, and to work together and with the people that actually can do the technical parts of the algorithms.
Okay, thank you. I have another question. What do you think of the future geoscientist or engineer? They would definitely be AI ready to be able to use these tools, or could they just kind of need to be trained up? I
think, well, I mean, it's hard to, they need to be, I think they would benefit them, and it would benefit their employers that they were ready, that they were trained at university in this. I don't know if that's going to be the case. You know, when I was in my last years in EQUINOR, I tried to find universities that were creating students like this, and there's really only a few at that time, which would have been 2017-18. Stanford is one, maybe some others, but not many. And boy, those students are very, very highly sought after, that have the combination of skills. So, you know, if you're a young person, I say, get the knowledge, get the training. And if you're older like me, I think it's almost impossible to get enough to do it, but it's, you can at least try and gain an understanding of why it's working, and be able to incorporate it.
Okay, thanks. We have a follow-up question from an earlier question. Why do you think the oil producing companies approaching the tech companies for AI development rather than enabling the development of AI within our industry, using the talent in our industry where there are domain experts?
Well, so the question is why are the oil companies going to the tech giants?
Yeah.
Well, I think that's just because that's where the true, if you saw the example I gave, that DeepMind and the ALPHAFOLD, that is from Google, a Google company. That's where the people are that really are developing the leading edge stuff. So, you know, not to denigrate anybody that's working with this within the industry today, but I think to making the big advancements, we do need to kind of delve in and partner with the tech companies.
All right, thanks. All right, we have someone with their hand raised. Let's see if we can move them so that they can ask their question.
I believe that Nazmul is already online.
Yeah. Would you
like to ask a question?
Yep, and I'm gonna unmute him. I'll try anyway. Well, it doesn't seem that I can unmute him. Maybe we're trying to unmute at the same time. All right, well, let's ask a question while I figure out how to unmute Nazmul. Thanks for your interesting presentation. Nowadays, oil and gas companies seem interested in migrating toward energy companies. In this transition, there isn't the risk of reducing the investments in hydrocarbon exploration. I guess, is there in this transition, is there a risk of reducing the investments in hydrocarbon exploration technologies?
I think it's a simple answer is yes, and it's not a risk, it's going to happen. It is happening. There are fewer investments, but that's why I say when we're doing, I still think we need to do exploration, but to get the money from the people that have the money, we need to show that we can do it even better than we have been doing it. So I think the competition for that money is going to be fierce. It's going to be even harder than it has been, and we have to really deliver on the investments that are made.
Erik, you have been working in different roles in both in the oil and gas companies and on the contractor side. So if you think about the recent events in the economy and their effect in reduction of personnel, and that you can see that as creating some gaps in the current workforce in the industry, also gaps in the students that are joining programs towards geosciences, etc. So the question is more about future students. Quite often we have a lot of students attending these presentations, and quite often we get the question of, would you recommend me to study physics or geophysics? Sorry, I'm a physicist. That was wrong. Geophysics or geosciences, or would you recommend that person to study something else and still keep an interest in this industry? Do you think that the mix that we have still in the workforce for the next, I don't know, 20 years will need more geophysicists, more geologists, or more people in computer sciences, or really that mix that you were talking about?
Yeah, I mean, I could kind of give a political answer. I can give what I think brutally honest answer.
I think the students will appreciate a more brutally honest answer.
Yeah, I mean, I don't want to discourage anybody. I think anybody that is truly interested in the geosciences should study the geosciences. People that have a true interest should study what they're interested in, and I think they will do well regardless. But I think that the industry is going to continue to shrink in terms of how many people the industry employs within the geosciences. It's a trend that's not going to turn around. And then I think that the people that are left, if you want to say, that do work in industry have to be, in my mind, have to be like the ones that I talked about on this team in some way, that they are really, really good at what they do. They have a deep discipline expert as a geologist or a geophysicist, and they understand other things as well. I think that machine learning is going to take away a lot of, eliminate a lot of, well, let's just call it routine work that you could fill your day with if that's what you wanted to do, and actually contribute to an overall effort. But that stuff is going to be gone, and what's going to be left, in my mind, if this all happens the way I model it, is that, you know, experts are going to be discussing very quickly models and scenarios that require a deep understanding of the physical processes. So I think that'll be really fun for people that, you know, are qualified to do it. I think that would be the best possible work environment. So, you know, if you truly are a dedicated geologist, stay with it, and just understand that I think, or at least this is my view of the way it's going to go.